In this lesson we are reviewing the polar form of a complex number. In the last lesson we looked at the standard form or Cartesian form of a complex number. In this lesson we're looking at the polar form. Both forms are useful depending on the type of situation we've got. So just recapping, in standard form we know that z was equal to a plus bi was the standard form of a complex number. Now I'm going to be using a diagram here. I'm going to try and draw a reasonably large one. Remember that on the argand plane, which this is called the imaginary axis, this is called the real axis. Now I might have a particular complex number here, z, might be plotted here. That is because its real component is a, so this distance out here is a, and its distance on the imaginary axis is b. So I could plot z here as being a plus bi. Now that's in rectangular form, standard form, or Cartesian form is what we've got there. But there's another way that I could actually represent this point. How else could I get to this point on my argand plane? Well, what I could do is pretend I was standing here at the origin. If I was told to turn a particular angle and then walk a particular distance, I could get to this point. So if I was facing in the direction of the real axis, I could be told turn so many degrees this way, anti-clockwise, and then walk a particular distance, I would get to z. So let's just draw that line in as how I would get there. That line there is the direct line from the origin out to that complex number. Now in order to do that I need two things. I need the angle that I've got to turn, theta, and we call that the argument of the complex number. We'll cover that in a moment. And then we've also got to walk a particular distance, or the distance from the origin. We call that mod z. Mod z, or the modulus of z, is and that's denoted with those vertical lines either side of the z. Also called r. R is also the symbol we use for the modulus of z. So there's two things here. We've got the angle and we've got the modulus. Now before we get too carried away with all sorts of mathematical rules that we need to remember this distance here is a. This distance here is b. So we actually, using the maths that we already know, mod z, or mod z written like that, or r, is equal to, this is just the hypotenuse of a right angle triangle, and we know the hypotenuse is the square root of a squared plus b squared. In other words, the absolute value, or the modulus, of a plus bi is equal to the square root of the real part squared and the imaginary coefficient squared, a squared plus b squared. Notice I do not include the I when I do the b squared, okay, because this distance here is b. That length is b, it's not bi. I just denotes that it's in the imaginary, on the imaginary axis. So the first thing we know is that mod z equals the square root of a squared plus b squared. Now, the other thing that I mentioned before, the other important component of this, is the argument. Now, we can use simple trigonometry here, and we can say that tan theta equals opposite. Tan theta equals opposite over adjacent, b over a. Therefore theta equals the tan inverse of b over a. And there we've got our angle theta. Now there's a couple of important points to note about the argument of a complex number. we say that arg z is equal to the tan inverse of b over a, where theta is measured from the positive real axis Now I'm assuming here that you remember some of your circle geometry and the way we label things. Typically, when we're doing complex numbers, we talk about the principal argument. And here I've deliberately used the capital A. The principal argument we call big A arg Z. And big A arg Z must be between minus pi and pi. In other words, and we'll cover this in other questions that we do further down the track. In other words, if I've got a complex number here, then what the principal argument says is, starting at the positive real axis, I always start with this one here, what's the quickest way to get there? Well, the quickest way to get to here is going that way. And so that angle, that might be 30 degrees or pi on 6, for example. If I have a complex number out here, the quickest way to get to it from the positive real axis, we always measure from the positive real axis, the quickest way to get there would be that way there. If I was to come this way around, it's going to be further. So the shortest way of getting there is here. So keeping in mind that this is pi, okay, and just let's pretend this is also pi on 6, that gap there, then this angle right around here would be 5 pi on 6, because this one here would be 6 pi on 6. Okay, so we're pi on 6 short of getting to there, so we must be at 5 pi on 6. So if our complex number was there, then our principal argument would be 5 pi on 6. Compare that, though, to a complex number down here. A complex number down in this quadrant. The quickest way of getting to that point is not going halfway around the whole circle, or more than halfway around the whole circle. The quickest way to get there would be coming this way. Now, as far as angles is concerned, going this way around the circle is actually a negative angle. And so let's say the actual size of this angle was pi on 6 or 30 degrees, then in this case capital A arg Z would be equal to negative pi on 6. Because according to the principal argument, it must be between minus pi and pi. It must be between minus pi, which is here, all the way around to pi, which is back here again. We might cover some of that in a further lesson to help you understand that when we do some specific examples. But in short, the most important thing you remember is that the principal argument is the angle. The argument is the angle. The principal argument is the shortest way, the quickest way of getting to your complex number. So if it's going positive around to pi, or it could be coming negative angles back to minus pi. Either way, you're getting there the quickest. So between minus pi and pi. Now, the last thing we need to do for polar form is, you may remember, I'll bring this diagram back, you may remember some basics from trigonometry. We know we could get a relationship between A, R and theta. We could say that cos theta is equal to the adjacent side over the hypotenuse. Therefore A, if we rearrange that, multiply both sides by r, A would equal r cos theta. You'll see that often happening in Math C. And we also know we could get a relationship for sine theta equals opposite over hypotenuse. Therefore B would equal r sine theta. Now remember these two things. I'll try and leave it there so you can see it. We know that z equals a plus bi, but we've now found both the distance from the origin, r, the modulus of the complex number, and we've found an angle. So instead of a, we could actually say a is no longer just a distance here. We can call it in terms of the polar coordinates of r and theta. R cos theta plus r sine theta multiplied by I. So what I've really got there is the a plus bi. Now we could take out a common factor here of r, and we'd get cos theta plus, and I'm going to bring the I in, I sine theta. I put the I in front of the sine, which gives us r, and mathematicians are great at shortcuts, the cos theta plus I sine theta we convert to cis. Now cis just stands for the C for cos, the I for the complex number, and the S for sine, r cis theta. So z equals r cis theta is a complex number written in polar form, where r is its distance from the origin and theta is its angle from the positive real axis. Some of the details of that we'll look at some specific examples in a later lesson.